In this tutorial, we shall analyze the linear thermal transmittance due to a corner joint, say between wall and roof. We shall continue to model the geometry from the previous video to create a roof slab over the wall. First, we delete the last block with color index 13 representing steel, which causes a point thermal bridge. Then, from the grids menu, choose to create minimum grid. At Z direction, we create 4 additional grids below, by first selecting the first grid mesh in the Z direction and then clicking on Insert after at the top toolbar. Now insert the mesh width as 10 cm for the first 3 newly inserted meshes, and 1 cm for the last mesh. At the blocks window, for first block with color 170, change the Y max limit to 5 and the Z max limit to 5. Now click the last block and choose Insert after to insert a new block at the bottom. For this block, input the color as 136 representing concrete, and for the grid domains, X min as 0 and X max 1, Y min as 1 and Y max as 5, Z min as 1 and Z max as 2. Now, at the blocks menu, choose Copy After. We notice that a copy of the block with similar grid domains have been created below. We change the Z min grid to 2 and Z max to 3. We now modify a few parameters of this block to create an insulation layer. Change the color input to 151. Similarly, at the blocks menu, choose Copy After. Now for the newly inserted copy, change the color index to 136. Then change the Z grid domain, with Z min as 3 and Z max 4. Now, we have created a model depicting a corner joint between the wall and the roof which causes a linear thermal bridge. Now, at the grids window, change the mesh width of the last grid to 100 cm. The distances of the flanking elements and the corresponding U values are essential in the derivation of thermal properties, in our example coefficient of linear transmittance psi value. The relevant standard for 2D and 3D thermal bridging EN ISO 10211 does not specify whether interior or exterior flanking element distance should be used. This is specified under national regulation. For example, in Belgium, the outer dimensions are applied. In the Netherlands and UK the inner dimensions are applied. Hence, you must be aware of which of this is to use as per your local standards. TRISCO is provided with an automatic algorithm to detect these surfaces and dimensions. However, it is important to understand and verify the used parameters. As you see in this picture, if we use external dimensions, the distances of flanking elements would be AB and BC. Whereas if we use internal dimensions, distances of flanking elements would be DE and EF. In this example the internal dimensions are lower than the external dimensions, hence the psi value would also vary based on the dimensions you use. Now, we see how to input this in TRISCO. At Settings, choose Flanking Elements. Here you can choose either the internal dimension or the external dimension. For our example, we choose external dimension. Now, at the Calculate menu, choose Initiate Areas and U value. You can double-check the selected areas via the Edit menu, choose Area. At the Area window we now see areas of wall and roof surface. Similarly, to check 1D U values, at the Edit menu, choose U values. Here you see the 1D U values across both the cross-sections of wall and roof. Once our geometry is ready, we split the grid at Grid menu and choose Auto Split. For smaller meshes up to 5 cm, we split into grid of 1 cm. For larger meshes, increasing the split ratio of 1.5. Now we have meshes created for analysis. At Edit, choose Derived Thermal Properties. Select Linear Thermal Transmittance. Finally, we run the analysis by clicking on Calculate. We now visualize the result of the analysis at the image window. At Text Output, at the Results tab, we get the values of linear thermal transmittance psi value. We now can close the text output. Thank you for watching, see you in the next video.